Today we're going to look at systems of linear equations in two variables. So we're going to talk about graphing systems of linear equations and finding a solution graphically and being able to test to see if a solution, an ordered pair is a solution to the system. We're going to solve linear equations by the method called substitution and another method called elimination. These two methods are algebraic methods that we can do by hand. We're also going to learn some technology methods using a TI-84 and Graphmatica, and basically where we find the intersection of graphs. And we're going to look at a couple of applications of this. So systems of equations are equations that are connected with an implied logical operator AND. So we're looking for points that make all of the equations true simultaneously. For this reason, sometimes they're called simultaneous systems of equations, or systems of simultaneous equations. The solution set to the system of equations is the intersection of the solution sets to the equations in the system. So for example, if we consider the system y equals 3x plus 2 and y equals negative 2x plus 7. So we're talking about equations with two variables. So these are going to be graphs in the xy plane. One way we can think of it, instead of thinking of it as, we can think of it as an intersection of the two things, or we can think of it as starting with the whole plane, the xy plane, and sort of erasing the things that are bad. The first thing, we erase the things that are not on that line, y equals 3x plus 2. And then the second hand, we erase things that are not on the line, y equals negative 2x plus 7. What we're left is only things that are on both lines. Or we're going to think of it the other way, is graphing both of these and seeing where they overlap. So each of these adds a restriction. So if we look at this graphically, here we see in red the graph of y equals 3x plus 2. So any of the points that are on that red line make that equation true. They're in the table for that particular relation. They are elements of that function. Now, similarly, the blue graph is y equals negative 2x plus 7, and we see that any points on that will make the second one true. Now what we want is the simultaneous system, so we want points where they're on both lines. And it looks like, from the looks of things, it looks like the point 1,5 visually is it. It looks like that's the only solution, and it looks like that is a solution, but it could be possibly just close to that, so we better check it to be sure. So if we check that in the first equation by plugging in 1 for x and 5 for y, we get 5 equals 3 times 1 plus 2. 3 times 1 is 3 plus 2 is 5, so we get 5 equals 5. That's a true statement, so that means that that point 1,5 is actually on the red line. Satisfies the red equation. Similarly, we're going to test it in the blue equation, y equals negative 2x plus 7. Plug in a 1 for x and a 5 for y. Negative 2 times 1 is negative 2 plus 7 is 5. 5 equals 5 again, and so that is once again true. So that says that that point 1,5 satisfies the blue equation, y equals negative 2x plus 7, so it's on the blue line. Since it satisfies both, it is on both lines, and it is in fact a solution to this system. Okay, let's look at a couple of algebraic techniques that we can solve for linear equations at least. And actually these general ideas that we're going to work with linear equations will generalize to other situations as well. The first technique is called substitution. So what we do here is we solve one equation for one of the variables. It could be either x or y, but we solve for one of the variables, and we substitute this expression for the variable in the other equation, reducing that equation, the resulting equation, to one variable. So solve this one variable equation, and then when you've got that value in hand, substitute it back into one of the equations with two unknowns and solve for the other unknown. So this general technique is called solving by substitution. Let's see it in action here. So see if you can apply the steps that we just said. Solve one of these for either x or for y. Substitute that. Say if you solve for y, substitute the expression you get in place of y in the other equation. Solve it for x. Back substitute it back into one of the equations with two variables and figure out the answer. and then you can check your answer as well. So why don't you go ahead and do this now. Press pause. Well, the first thing we wanted to do was to choose a variable to solve for. Now we can effectively solve this by solving for either x or y, starting from either one of the equations. So we actually have, 4 possibilities. Solve the first equation for y and substitute in the second equation. Solve the first equation for x and substitute in the second. Or we can solve the second equation for x and substitute back in the first. Or we can solve the second equation for y and substitute back in the first. So, since we can do it any one, we're going to take the easiest path. Which one would that be? Well, it looks like to me the easiest thing to do is to solve the second one for y, because all I have to do is add negative 2x to both sides and then divide both sides by negative 1 to get y equals 2x minus 11. Now what we want to do is, this is what y is if you're on the second line. But it's the same y if it's a solution to the simultaneous system. So the y, this is the value of y that we can plug in place of the other equation. Now, by the way, look what happens if we plug back into the same equation. If we plug this back into here, it's going to to the second equation, it's going to reduce to 11 equals 11, which is certainly true but not helpful in narrowing things down. So what we want to do is take this 2x minus 11, put it in place of the y in the other equation. So we have 3x plus 2 times 2x minus 11 equals 7. So now this equation only has one unknown. We want to solve this for the unknown. So if you haven't done this already, why don't you stop here and go ahead and do this now. Press pause. So solving this is just using the distributive property. 2 times 2x is 4x, and 2 times negative 11 is negative 22. Combine like terms, 3x plus 4x equals 7. Add 22 to both sides to get 7x equals 29. Divide both sides by 7 to get x is 29 sevenths, or in decimal form, 4.142857, and then the 142857 repeats. Now once we have x, how can we find y? Take this x and take any one of these equations, the original two or this one solved for y, and plug the 29 sevenths in place of the x, say in this one or this one or this one, and then solve the equation you have for y. So this one's already solved for y, so I just used it. So I'll let x be 29 sevenths here, and 2 times 29 sevenths is 58 sevenths, minus, and then get a common denominator, 11 is 77 sevenths. 58 sevenths minus 77 sevenths is negative 19 sevenths, or negative 2.714285 with the 714,285 repeating. So now let's state the solution set, or just state the solution, which is just one thing, 1 point. The ordered pair xy is 29 sevenths, comma, negative 19 sevenths, or here it is in decimal form. Now we can substitute back into both of the original equations to check, to make sure. So we take 3x plus 2y equals 7, put 29 sevenths in place of x and negative 19 sevenths in place of y, and we distribute, we multiply here out, and then since we already have a common denominator, we can add those together and reduce, and we get 7 equals 7. This is a true statement, so that one checks. Similarly, we check it in the other equation, which you can see worked out there. So since it checks in both equations, it is a solution. And in fact, since these are lines, of course, this is going to be the only solution. So here's one for you to try now that you've seen an example. Do this one on your own, and then come back and check it when you're through. Press pause now. Okay, so here's everything worked out. First on the left, you see where we first we solve for y in the second equation. I chose to do it that way. I could have sought, there's 4 possibilities here. Any would work. So we add 3x to both sides and divide both sides by 2, and so y equals 3 halves x plus 4. Plug that in place of y in the other equation. Be sure you're putting it in the other equation, which gives us this expression here, 4x plus 7 times 3 halves x plus 4 equals 55. Distribute the 7, And now I have fractions here, so I'm going to get rid of the fractions by multiplying both sides of the equation by 2. And I distribute that. That gives me 8x plus 21x plus 56 equals 110. That saves me from doing some fraction arithmetic. Combine like terms here is 29x and subtract 56 from both sides, and then divide by 29 to get the final answer for x. Now once I know x, I can plug that back in place of y, back in place of x in one of the original equations here, or this version of the original equation here, by plugging it in place of x here. I can plug it back into any equation that has both x's and y's to solve for y. So when x is 54/29, multiply by 3 halves, that's 81/29. Get a common denominator here and add these up. And now we've found both x and y. Now we want to check, we should check this solution, and I'm going to actually check this using a calculator and show you something that we can do here. This may take me just a second to pull my calculator up. Let me show you a nice little way to check this. So 54, let's clear that out. Okay. So 54/29, store that as x, and this will give is a decimal. So there it is, rounded off, and we see that the decimal version matches up with that. And then let's take the 197/29 and store that as alpha y. And now if I do 4x plus 7y, it should be 55. 4x plus 7y, and hopefully that's 55. Yes, good, that checks. And if I do negative 3x plus 2y, hopefully this one will check as well. And that's supposed to be 8. That's what it's supposed to be. And so that checks. So if you have your calculator with you, it's a very quick way to check an equation. And notice I just stored my variables as x and y, and then I just typed one side of the equation. It should be the same as the other side of the equation. So it's a nice little way to check with the calculator. Of course, I could have checked this by hand by plugging these into both equations and working them out and making sure it worked out correctly. Alright, here's another system, and this time we're going to solve by a technique called elimination. Now what we're going to do here is we're going to just add these together. Now if we take that first equation, 3x plus 2y equals 21, both sides of that equation are actually 21. They're the same thing. Of course the right side is just 21. The left side's an expression that's equivalent or equal to 21. Similarly, the second equation, both sides are 17. So if I take the original equation and add 17 to both sides of the equation, it's going to still be a true statement. So I add 17 to the right side and get 21 plus 17 is 38. But when I add 17 to the left side, instead of using 17, I'm going to use the equivalent expression 2x minus 2y. And now look what happens. The 2y and the negative 2y cancel out, and we get 3x plus 2x is 5x. So the resulting equation right here is 5x equals 38. Well, that's an equation with only one unknown. It's fairly easy to solve just by dividing by 5. And so we get x is 38/5, or 7.6 in decimal form. Now, one thing we could do, there's a couple of options here, but one thing we could do is take this x now and back substitute. That is, go back to one of the original equations, either one, I chose the second one, and put that in place of x and then solve for y. Which you see I did here. Multiply 2 and get 76/5. I multiply both sides of the equation by 5 to get rid of the fractions there. I should use the distributive property on the left. And then add negative 76 to both sides and then divide by negative 10. And we get y is negative 9/10 or negative 0.9. And so we get that. Let's check that one just to make sure I didn't make any mistakes here. Okay, and again, I'll use the same technique I did a minute ago. So 38/5, store it as x, And by the way, this will check my decimal version, 7.6, that's good. And then negative 9/10 store as alpha y, and that's negative 0.9. That looks good. Okay, now let's see if it works in the equations. So 3x plus 2y, hopefully this is going to be 21. Good, it is. And 2x minus 2y, what do we want this one to be? We want it to be 17. Yes, it checks. So it checked in both equations. And we could have done that same check by hand. Now I want you to solve this equation here using the same technique. However, this one puts a little bit of a wrinkle into it. If we just add these together, nothing cancels out. We get 7x minus 2y. So that's not exactly what happened over here. Here when we added them together, the y's canceled out. Can we do something to these equations, one or both equations, to manipulate it so either the x or the y is eliminated? See if you can figure out what to do with that. Work it out and then come back. Press pause now. Well, one thing we can do is multiply both sides of equation by a non-zero constant. So if we multiply equation 1 by 3 on both sides, distribute on the left, we get 15x plus 3y equals 75. And then leave equation 2 alone, 2x minus 3y equals 17. Now, look what we're trying to do. We're trying to adjust so that the coefficients of one of the terms, in this case I decided to eliminate y, so it's the y term, I want to have the opposite coefficients so that when I add them together, look what happens, the y's cancel. And we get 17x equals 92. That's easily solved for x. Now at this point I have two options, okay, to solve for. I know what x is, I can solve for y. I can either do what I've done before, back substitute, take this x and place it in place of one of these x's up here and solve the resulting equation for y. Or I can do the same technique that I did here to instead of eliminating the y's, eliminate the x's. So let's do it that technique to practice our elimination. This time eliminate the x's and solve for y. Go ahead and do this now. Well, we need to bump these up. 5 and 2 are the coefficients. We need to bump up to a common multiple. Say the least common multiple would be 10, and I need to make one of them 10 and one of them negative 10. So if I multiply equation 1 by 2, that'll give me a 10x, and then I need to multiply equation 2 by negative 5, that gives me negative 10x. So, what does that give us for the rest of the equation? Well, if I multiply the 5 by 2, I've got to multiply that whole equation by 2, both sides of the equation, and distribute on the left. So basically multiplying each term by 2. So I get 10x plus 2y equals 50. And when I multiply negative 5 times equation 2, I get negative 10x plus 15y equals negative 85. This time when I add them together, the x's cancel and the y's add up to 17y, and the constants are negative 35, and so y equals negative 35 over 17. Now we have both x and y. Go ahead and state the solution and check it. So the solution is actually an ordered pair. xy equals 92 over 17, comma, negative 35 over 17. And here's a calculator check doing it the same way that we just did our last couple of checks. So what do we do when we solve by elimination? We manipulate the equation so that all the variables are on one side of the equation, all the constants are on the other side. We do that first. Then we multiply both sides of one or both of the equations by a constant, a non-zero constant, to get the coefficients of one of the variables to be opposites. Then we add the two equations together to eliminate that variable. We solve the resulting equation with one variable for that variable that's left. And then we have two choices. We can either substitute this value into an equation with both variables and solve for the other variable, that's called back substitution, or we can use the technique of elimination again to eliminate the other variable from the original equations in the same manner that we saw for the other variable. So let's go ahead and try this again. Another example for you to try on your own. Do this by elimination, solve it, and then check it by hand and with your calculator. Okay, so if we want to, first I want to eliminate the y's. I've got coefficients of 5 and negative 4. I need to bump them up to 20 and negative 20. So if I multiply equation 1 by 4 and equation 2 by 5, I believe that'll work. 4 times equation 1 is 8x plus 20y equals 52. And 5 times equation 2 is 15x minus 20y equals 110. Now when we add together the y's cancel and we get 23x equals 162, or x equals 162 over 23. Then I'm going to solve for the y by eliminating the x's. Multiply the first equation by 3 and the second one by negative 2. And let's see, 3 times the first equation is 6x plus 15 equals 39. Negative 2 times the second one is negative 6x plus 8y equals negative 44. Add together, we get 23y equals negative 5, y equals negative 5/23. So our answer is xy ordered pair equals 162 over 23, comma, negative 5 over 23. And you can see that it does check out using the calculator. Of course, you can check by hand as well. I just wanted to show you the calculator way of checking as well. Now, we also have another method where we can solve by intersection of graphs. We've been doing intersection on graphs on our calculators for a while now, so this should be no news to you. You should have realized that you could do this. Now, to get them in the calculators, if it's like a TI-84 and Inspire, you have to solve for y, get it in the form y equals first. So solve each equation for y and enter the equations in the graphing window as y1 and y2. You want to graph it, and you may have to adjust the window to see the point of intersection. Choose Calc, which is second trace, and then go down to number 5, or just hit 5, which is intersect. It's going to ask you for the first curve. If you only have 2 curves graphed, just hit enter, enter, and then move your cursor to the guess and hit enter. If you have several things graphed at the moment, remember you have to identify which 2 curves. So use your up or down arrows to choose curve 1, hit enter. Up or down arrows if you need them to choose curve 2, hit enter. And then move your cursor close to the point of intersection using the left or right arrow, and then once you get there, hit enter. It will give you the x and y coordinates, at least decimal approximations for those. Press quit, which is second mode, and then hit X, and then type X, and then do math, and then enter, and then enter again, and that will change it to a fraction. And if you do Y, alpha something is Y, and then that will give you the letter Y, and then type math, and then enter again, or press the math button, and then enter twice. And that'll give you a fractional answer for y if it's possible to get a nice fraction for it. So the change to the fraction thing's not perfect, but if it's a fairly reasonably small denominator, it will figure that out for you. So let's try this method on a TI-84 with these this system of equations. And then go back and check them with your calculator the way we did earlier. Go ahead and press pause now and do this. Well, the first thing is to solve for y. So the first one, we add negative 5x and divide by 2 to get y is negative 5 halves x plus 11 halves. And the second one we solve for y is 3/5 x minus 2. So you do have to do some algebraic manipulation just to get it in your calculator. And you can see how I've typed those in the calculator. Then I just did a zoom standard, and the zoom standard happened to show the intersection, so I was good with that. So zoom standard is this window here. And did that. Then I want to calculate and do number 5, which is intersection. First curve came up somewhere, I just hit enter. Second curve was it switched curves, so I just hit enter. Then I move my guess close to the point of intersection, hit enter, and it gives me that value of the intersection. If I come back to the home screen immediately and type x, change to fraction, it was 75 over 31. and y changed to fraction was negative 17 over 31. So 75 over 31 stores x, negative 17 over 31 stores y, and if I do 5x plus 2y, it is 11, and 3x minus 5y is 10, so it does check. If you're going to do this in Graphmatica, there's some good news and bad news. The good news is it's a little bit easier to do in Graphmatica. The bad news is the Graphmatica doesn't have the change to fraction feature. It's only going to give you a decimal approximation. It doesn't show you quite as many decimal places as the calculator does, but it's actually a little bit easier to do. Because, number one, to put your graphs in, you don't have to put the formula in y equals form. You can just type it in the way it looks. So it saves you that step. And you still want to graph both of the graphs. Make sure that the window has the appropriate intersection point, and you choose from the drop-down menu, choose Tools menu, and then Find Intersection, and you'll have dialog boxes there that you can choose your two curves, and then hit I think it's Calculate, and it will give you the approximation of the points. So try that in Graphmatica with this example here. 4x plus 7y equals 5, and 3x minus 8y equals 2. Press pause now. Okay, so with Graphmatica, you're going to just graph this, and you can see I typed in 3x minus 8y equals 2, hit enter, and before that I'd already typed in 4x plus 7y equals 5, and enter. Just enter them like they are, and the first one, so we have these here. The second one is the light blue, and the first one is the dark blue. And there's the intersection point. So then I go to Tools, hit this Tools, and down one of the choices is Find Intersection. And notice it has my two equations up. I don't have to do anything because it's already pulled them up there. But if I had a big list here showing on the screen, I could use this thing here to choose the ones I'm interested in. And then just hit the button Calculate, and it comes back with these values here. Now, in fact, this has a fraction answer, but these are rounded off, so it's likely, it very likely could be maybe a repeating decimal or something, and so these are not exact values. For linear equations, and where the coefficients are natural numbers or even rational numbers, the calculator is going to be able to tell you an exact value in fraction form if we remember to do that change to fraction thing at the end. So here's another one. Go ahead and do this one, please. Press pause now. When we come back here, what we notice is when we graph it, we get parallel lines. There is no intersection. And algebraically, we can see that. This one's already kind of set up to do substitution, so I'm going to use that method. So y equals negative 2x plus 1. Plug that in place of y in the other equation. Be sure it's the other equation, not back in the same one. But put it in the other equation, and we end up solving that. We get something that's not true. 2 equals 7. That's false. That's a contradiction. So the solution set is the empty set, which is denoted by this symbol, which means that when you graph it, your graphs are not going to cross. Since these are lines in a plane, that means we have parallel lines. Try this one. Press pause now. Well, when we do this one and we solve again by substitution, we get a statement that's always true. Negative 8 equals negative 8. Once again, be careful, because if I were to substitute back into the same equation, I'll get a similar thing, like 4 equals 4. Okay, or negative 8 equals negative 8. But if I substitute in the other one, in this case, it still gives us a statement that's always true. So this says that there are infinitely many solutions. We call this a dependent system. The one where there's no solution we call an inconsistent system. So the solution set is actually a whole line. What it really have is we got the same, these are two different looking equations, but they're really just two forms of the same function. So they're the same graph. It's the same line twice. So the solution set is just this one graph, this one line. So there are infinitely many solutions, but they're not just anything. And so we could say x, y is an element of the set x, 3x plus 4, such that x is a real number. And so we should be able to do this, write it in terms, either in terms x in terms of y or y in terms of x. And our standard way is y in terms of x. And so see how we've written our solution set there. A little more complicated way of writing the solution set because it's not just one number. There are infinitely many things. X can be any real number, but once x is fixed, y has to be 3 times x plus 4. So if you notice, when we have two lines, the system of two linear equations and two variables, there are three possibilities for the solution set. Either no solution, one solution, or infinitely many solutions. First, you could have what's called an inconsistent system. The graph is two distinct parallel lines, and the solution set is the empty set. We could have what's called a consistent independent system. The graph is two distinct intersecting lines, and the solution set will be a single point. We'll write our answer as the ordered pair xy equals some specific ordered pair, like xy equals the ordered pair 3, 4. Okay? Or xy equals sum AB for some specific A and B. We can also have a consistent dependent system, and for the graph it's the same line twice, so the solution set is just a graph, and whereas the solution set on the middle one was just a single dot and nothing at all for the first one. This time the solution set is a whole line, and so it's infinitely many points on a line, and we write our solution set as xy is an element of the set x, comma, mx plus y sub 0, close parentheses, such that x is any real number. And of course the equation of our line is y equals mx plus y 0. Again, the m and the y 0 are specific numbers. Alright, now I'm going to look at a couple of examples now where we can apply this in a real world situation. Okay, step 1, read the equation. An airplane flies a 3,000-mile trip from Los Angeles to New York with a tailwind in 5 hours and 15 minutes. The return trip is against the wind and takes 6 hours and 30 minutes. What's the speed of the plane relative to the wind, and what's the speed of the wind? We're going to assume the plane's speed relative to the air is the same the whole time, and that the speed of the wind is the same all the time for the whole trip. Okay, let's see what we need to do here. Well, we're going to let P be the speed of the plane relative to the air, and W be the speed of the wind. And 3,000 is the distance traveled both directions. So the trip with the wind, that is Los Angeles to New York, okay, is going to be, we're going to have the rate of speed relative to the ground times the time in hours equals the distance in miles. So what we have with the wind is we have the speed of the plane plus the speed of the wind. So that's P plus W is the speed relative to the ground. So we multiply those together and we get 5.5 times P plus W is the distance traveled on the way there. On the way back from New York to LA, we're going against the wind. We're assuming the same wind speed, so it's still W. Same plane speed relative to air, and so that's P minus W for the speed relative to the ground. And the time it takes is 6.5 hours. The distance covered then is 6.5 times P minus W. And both of those are 3,000. So our equation then, our system of equations is that 5.25 times P plus W equals 3,000. And 6.5 times P minus W is 3,000. Now what I'm going to do now is actually divide both sides of the original equation, first equation, by 5.25, and the second one we're going to divide both sides by 6.5. So this solves for P plus W and P minus W, which are actually the speeds relative to the ground. So this 571.42, etc., that we get, let's say about 571.4, that's actually the speed that the plane is making relative to the ground on the trip from LA to New York. and the 461.5 is actually the speed relative to the ground that the plane's making on the trip from New York back to LA. And these are already set up to do elimination. Just add them together, and we get 2p equals 1032.967033. Divide by 2, we get p is about 516.5. Okay? Now, we can substitute this back into the equation, p plus w equals 571 point something, and solve for w to get w is about 54.945. So, we've done step 3, set up the equation. Step 4, where we solve the system of equations, actually. So we set up a system of equations here and solve. So step 5, the speed of the plane relative to the air is 516.5 miles per hour, and the speed of the wind is 54.9 miles per hour. It's going to be appropriate to round off at some point, and I'm not sure what exactly the best point is here, so I just chose tenths here. So in step 6, we're going to check it. Notice that p plus w, we've already found that, is 571.4 miles per hour. That's the speed relative to the ground. And they did that for 5.25 hours. Oh, by the way, notice I had to convert 15 minutes to a decimal part of an hour. 15 divided by 60 is 0.25. And then multiply those together. 571.4 miles per hour times 5.25 hours equals, well, right at 3,000 miles as needed. And p minus w is 461.5 miles per hour times 6.5 hours is, again, about 3,000 miles. The round off is there is because I rounded off my answers a little bit. Okay, so that does check out, and there we have the correct answer. Okay, one more example. When a product, whether that's goods or services, is provided, the price and quantity available are related to each other. There are separate functions that describe the behavior of the relevant parties. Economists write both of these relations as the unit price P is a function of the quantity Q. Even though we maybe think of it the other way around, they'll write P as the horizontal axis, Q as the vertical axis. So, demand function describes consumer behavior. The higher the price, the fewer items the consumers will demand. It's a decreasing function. Let me see if I can explain this a little bit. Let's say that I was selling calculators, and we take all of you guys that are in this class, and let's say at the beginning of the semester you might want some calculators. Well, what if I sold them for $10 each? Well, probably everybody would buy, say, a nice new TI Inspire for $10. That's way under the normal price. So I would have a real high demand. So collectively, you guys would demand a bunch of those calculators. But as I raise the price, maybe to $50, then some of the people would still want one, but not as many. And so the demand goes down. And if I raise the price to $100, now the demand goes down. Still a good deal for that calculator, but the demand goes down some. When I reach the normal selling price, now the demand's going down further. If I raise it above that, now the demand's going to go down even further still. Okay? The supply function, on the other hand, describes the producer or the supplier's behaviors, collective behavior. So the higher the price, the more items the producers will be willing to supply. So this one's an increasing function. Okay, so let's do it this way. Let's say all of you guys have a graphing calculator. How many of you would be willing to sell me your calculator for $10? Well, not many. Maybe none. What happens if I raise it up? 20, 30, 40, 50. At some point, maybe you're willing to sell it and to trade up to a newer calculator or something. Okay, once I get up to the price more like the real selling price of the calculator, a bunch of you are willing to sell it. So collectively, this time you're the suppliers. Okay, and so you're more willing to supply me calculators collectively, the more I'm willing to pay for them. So let's pretend for a particular product the supply and demand functions are P equals 250 plus 30Q and P equals 500 minus 25Q. So the first question is which one's supply and which one's demand, and how do you know? Then we want to choose an appropriate window and graph these two functions. Now what happens is if you're left alone in a free market economy, the price and quantity will stabilize and settle to the intersection point of these two graphs. This is called the market equilibrium point. We want to find that XY coordinate or a QP coordinate and interpret it. Q is the horizontal axis, P is the vertical axis. Go ahead and do this now. Well, the first thing is notice that the first equation is got a slope of 30, so that's a positive slope. That's an increasing function. That's going to be the supply curve because the supply curve is always increasing. And the second one has a negative slope, negative 25, so it's decreasing, and that's a demand curve. The demand curve is always a decreasing function. Now, what kind of window would be appropriate here? Well, first of all, Q is the quantity. That can't be negative. P is the unit price. No, that can't be negative either. So we're talking about a first quadrant graph only. These functions don't make sense anywhere outside of the first quadrant. Now, okay, so we know X min and Y min are both going to be 0. What about X max and Y max? Well, if you look at the demand curve, it starts at 500 at the top and then descends from there. So maybe we want to start, we want to go up to 500 for Y. Alright, and if you look at that demand curve, it's going to hit the x-axis when X or Q is 20, if you put P as 0 in that and solve. And so that tells us if we use the window 0 to 20 by 0 to 500. So notice that's X min to X max by Y min to Y max. This is one way we might write the interval right here. And I'll show you the graph on the next page. So let's solve this. I'm going to solve it by hand. It's set up to do substitution very nicely, and so substitute this bottom one in the left side of the right one, or vice versa. So we get 250 plus 30Q equals 500 minus 25Q. I'm going to add, let's see, add 25Q to both sides. That gives us 55Q on the left. Subtract 250 from both sides. That gives us 250 on the right. And divide by 55. That's 250 over 55 reduces to 50 over 11, or 4.54 with the 54 repeating. And I'm going to do it by back substitution this time. I'll let the Q be 50 over 11, and I substituted into, well, either one. I did the supply curve. Put it 50 over 11 in place of Q. Solve that for P, and we get P as 4,250 over 11, or 386.36 with the 36 repeating. Okay, so if we sort of round this off, P is the unit price at the market equilibrium point. So that's the Y value of that curve, and so that is $386.36 per item. And how many items? Well, about 4.54 items. Can you have 4.54 items? Well, it depends. Some things are discrete and you can only have a whole number of items. Others, there could be decimals depending on what it is. So here's the graph using Graphmatica. And I went ahead and Graphmatica went ahead and did the calculate intersection to make sure it checks out right, and it did. And so there you can see it, and that's the window we talked about using. Here it is on your calculator. Put y1 is 250 plus 30x, y2 is 500 minus 25x. Again, you can see the window I chose, 0 to 20 and 0 to 500. And then I did a calculate intersection, and you can see that intersection point there. And there's our interpretation. So, what should you be able to do now? You should be able to solve some systems of linear equations by hand by the substitution or elimination method. You should be able to graph them by hand or with the technology. Once you've got them graphed with technology, whether it's on your graphing calculator or on Graphmatica, you should know how to use the technology to calculate an intersection point. You should be able to do this in application problems, be able to set up some system of equations and then solve them using these techniques.